Hey guys, welcome to Unit 1.2 Video 12 for Mr. McGee's 9th grade biology class at Arizona School for the Arts. This video series follows the biology coloring book by Robert D. Griffin, and today we're going to take a look at protein structure. Before we begin, I'd like to do a couple things. First of all, review notes from Video 11, specifically regarding proteins and amino acids. And then please make a chart that looks like this. And while you're doing that, I'll introduce you to some of my cats. Our first cat is Gigi. Second cat is Calcifer. Here's Gandalf the Grey. Gandalf the White. Laszlo. Archer. The twins. Triplets. Frosty. Marmalade. Blackie. And that's it. Oh, one more, Tiny Tim. So let me just get my chair in the right position here, and oh my god! Oh my god! Okay, so proteins, right. Proteins are very complex. They're not just long chains of amino acids, that's part of their structure, but once you have a long chain of amino acid, it automatically takes this very elaborate 3D structure. It takes the shape of folds and loops and clumps and sheets and all kinds of other structures. Because remember, many proteins are things like enzymes that have to perform a task like a little molecular machine. So they've got to have this complex structure. Protein structure involves 4 different levels, and they're right here: primary, secondary, tertiary, quaternary. So you should have those in your chart by now, which is great, which means we can move on. So let's take a look at each of these levels of structure right now. The first level of structure is called primary structure, and it involves just the sequence of amino acids in the polypeptide. So here's an example on the slide. 4 different amino acids, all of them linked together through dehydration synthesis, and what you end up with is each amino acid is bonded to the other by a peptide bond. If you don't know what a peptide bond is, you need to go back to the last notes from the last video and review. Secondary structure involves the formation of twists and sheets, and it's primarily created by H-bonds. Our old friend, the H-bonds, they're back. Looks like this. So there's 2 types of secondary structure that are important. The first type is called the alpha helix because it's the first type of the 2 structures to be found. So it gets the designation alpha. The second type of structure of proteins to be found is called the beta pleated sheet. It's where the amino acids sort of make these folds and they link together in several rows to make a thick sheet. Where are the H-bonds? Well, they're all over the place. Both alpha helixes and beta pleated sheets are rich with H-bonds. There's H-bonds between hydrogen and oxygen throughout these 2 structures. Tertiary structure is where you start to see the overall shape of the polypeptide. And there's all sorts of different kinds of bonds involved. And we'll just take a look at, I think, 4 of them. So here's what you might see if you're looking at a long chain of amino acids. That's what this purple ribbon is supposed to represent, a long polypeptide. And there's lots of different kinds of bonds that hold it together in this structure, in this 3-dimensional arrangement. The first is hydrogen bonds. So once again, hydrogen bonds playing an important role in biology. So you know what hydrogen bonds are. You see that one part of the amino acid has an H, and the other amino acid across from it has an oxygen, and you know that those are going to be attracted to each other because of the slight difference in their charge. There's also ionic bonds. So remember, our amino acids can have a positive or a negative charge. An ionic bond is what is formed between amino acids that are positive and amino acids that are negative. So you could have an elaborate structure that's held together pretty securely by the ionic charge between the 2 types of amino acids. We call that an ionic bond. There's also disulfide bridges, which is just a fancy name for a type of covalent bond that happens between 2 amino acids of cysteine. So if you take a look at this picture, there's a little yellow bar that shows you that there's 2 S's. That S stands for sulfur. Sulfur is one of the atoms that's found in amino acids of cysteine, and they form a covalent bond between the 2 sulfurs. So that's why it's called a disulfide bridge. The final kind of bonding is a little bit confusing. It's not a true bond. It's called a hydrophobic bond, or sometimes it's just called a hydrophobic interaction. And this is where part of the structure of the protein is stabilized by amino acids that are nonpolar. And remember, if they're nonpolar, then they must be hydrophobic. Hydrophobic things clump together in water. Remember back to the experiment we did with the oil droplets in water. Why do they form those spherical structures? Why do the little bubbles come together and join to make bigger bubbles? Because of hydrophobic interactions. Nonpolar things clump in water. These amino acids are nonpolar, they clump. So they're held together by a very, very weak form of attraction called a hydrophobic bond. Finally, if you have quaternary structure in a protein, that is produced by a combination of 2 or more polypeptides. So far, we've only looked at the type of structure that is involved in a single polypeptide chain. But lots of proteins are made up of multiple polypeptide chains that are put together independently to make a single functional protein. A good example is hemoglobin, the protein that carries oxygen in your blood. It's made of 4 separate polypeptides that are then bonded together to make the functional protein hemoglobin. And quaternary structure involves all of the bonds that we've previously discussed. So H bonds, ionic bonds, disulfide bridges, hydrophobic interactions, you name it, those bonds are involved in quaternary structure. This is what hemoglobin looks like. Isn't it awesome? The red part on the left is a separate polypeptide chain from the red part on the right. The blue part on the left is separate from the blue part on the right. That's 4 different polypeptide chains. They all have to be put together to make one functional protein. And if you notice, there's some little green things in there. Those are non-protein components of this working protein. So those have to be added to before hemoglobin is able to do its job of carrying oxygen. So, 4 levels of protein structure in every single protein. Well, that's the end of this video. Please complete the corresponding review questions and be prepared to show your notes in class. And, wait for it, here's your bunny of the day.